Estimating a population mean and the t-distribution. The point estimate for the population mean mu is the sample mean x bar. Recall, each sample is likely to produce a different mean, even if the sample sizes are the same and we're obviously sampling from the same population. So just as we did with the population proportion, we create a confidence interval to estimate the population mean. That confidence interval will be the point estimate plus or minus the margin of error. So our point estimate x bar plus or minus the margin of error e. Alright, the sample mean x bar distribution will be normal if the population from which the sample is drawn is normal, or the sample size is greater than or equal to 30. So we've got x bar plus or minus the critical z-score sigma over the square root of n. And keep in mind that the mean sub x bar is equal to the mean, and sigma sub x bar is equal to sigma over the square root of n. This presents a major problem. We need to have the population standard deviation to construct the interval, but how do we have the population standard deviation if we don't have the population mean mu? If you recall at the beginning of the semester when we started learning how to calculate these, we had to actually have the mean in order to calculate the standard deviation. So this creates a situation where we need information that we actually don't have to find what we're searching for. Alright, so an option is to use the sample standard deviation in place of sigma. So that would lead us to x bar plus or minus z sub alpha over 2 s over the square root of n. But this creates another problem. Just as x bar will vary with each sample, so will the value of s. So with these two things varying so much, we don't have enough to account for that variability in each sample. Okay, using the normal distribution doesn't take into account this additional variability. So we've got a new model that we need to use when we're estimating the population mean, and it's called the student's t-distribution. The student's t-distribution is supposes that a simple random sample of size n is taken from a population if the population from which the sample is drawn follows a normal distribution of t equals x bar minus mu s over the square root of n. This follows the student's t-distribution with n minus 1 degrees of freedom. So degrees of freedom we will abbreviate as df, and that is equal to n minus 1. That's the sample size minus 1. X bar is the sample mean, s is the sample standard deviation. Now think about degrees of freedom like this. Let's say we had 30 students in a classroom with 30 chairs. Okay, the first student who walks in has 30 choices or freedom to sit in 30 different places. The next person who walks in has 29 choices or the freedom to sit in 29 different places. So if we have 30 students, all but that 29, that last student is going to have a chance to pick where they want to sit. So 29, n minus 1, students would have a choice of where to sit. So there's how many degrees of freedom there would be in that situation. Alright, so the t-distribution is very similar to the normal distribution. However, the t-distribution is different for different degrees of freedom. The distribution is still centered around the mean. It's going to have actually fatter tails than the normal distribution, but it's still centered around the mean 0. The area under the curve is still 1. The area under the curve to the right of 0 equals the area under the curve to the left, which is a half, so we still have the symmetry. As t increases without bound, the graph approaches but never equals 0. As t decreases without bound, the graph approaches but never equals 0. So similar to the normal distribution. The area in the tails of the t-distribution is a little greater than the area in the tails of the standard normal distribution because we're using s as an estimate of sigma, thereby introducing further variability into the t-statistic. So the t-statistic you're going to find at the same level of confidence is going to be larger than the z-score at the same level of confidence. Okay, that's going to give you a larger margin of error so that you are accommodating that variability from your samples. Okay, as the sample size increases, the density curve of t gets closer to the standard normal curve. This result occurs because the sample size increases, the values of s get closer to the value of sigma by the law of large numbers. So remember when we were dealing with z sub alpha, that implied that alpha was the area to the right of the z-score. So t sub alpha will be the same. Alpha is the area in the right tail. Now we have a t-score table, and you'll notice that this table only deals with the area in the right tail. So this is actually alpha, and this is t sub alpha. Oh, alphas don't look pretty. Let's try that again. Alpha, and this is t sub alpha. Now, this table is different than the normal distribution table. Here we've got degrees of freedom going down the left-hand column here. It goes in equal increments until you get to number 40. Then it skips and goes 50, 60, 70, 80, 90, 100, 1,000, Z. So it skips to what the Z-score would be at that value, because at that point the sample size is large enough that it's starting to mimic the normal distribution. Okay? This one gives us the area in the tail, in the right tail across the top, and what's in the body this time are the actual t-scores. Okay, so it's totally different than the normal distribution. Okay, in the body of the normal distribution table was the area, and along the sides were the z-scores. Alright, so let's look at an example of how we're going to use this. And this is going to be the one thing that varies in finding our critical value. Okay, so t sub alpha over 2 will be our critical value. At this point, we're just looking for t sub alpha, and alpha is the area in the right tail. Remember, with critical values, we had alpha over 2 because that was the area split up into 2 tails. Okay? So it says, assume n is 17, find t sub 0.10. So that means we've got a degrees of freedom of n minus 1. So 17 minus 1 is 16. So I'm going to go to the table, and I'm going to go down to degrees of freedom of 16, and I'm going to go across to an area of 10. So where these intersect gives me my t-score of 1.337. So my t-score is 1.337, I believe. Yep. 1.337. Alright, assume n equals 30. Find t sub 0.05. So if we think about what this meant here, if we just drew that out before we go any further with this one, this means we've got the t-score here, and this is 10% of the area is in the right tail. So it turned out that t-score was 1.337. Alright, now I want to find the t-score. So that 5%, this is t, this is 0.05. I want to find the t-score so that 5% is in that right tail. The degrees of freedom is n minus 1. 30 minus 1 is 29. So we're going to go to the chart. 29 and 0.05. So we go down to 29. 0.05 is this column. I'm just going to have to drag it to see. So 29 and 0.05 gives me 1.699. So this t-score is 1.699. Alright. Now we're looking for t sub alpha, and alpha is 0.001. Looking for the t-score that makes that happen. The degrees of freedom is n minus 1. 40 minus 1 is 39. So 39 and 0.001. Let's clean this up here. 0.001 is this next to the last column here. And I want to go down to 39. So I'm going across 3.313. Okay, so my t-score is 3.313. Let's go in here. Oops. Well, I need to behave a little bit here. Okay, so now I'm looking for the area in the right tail. Okay, this table always deals with the right tail. If you're interested in the left tail, you just have to change the sign of the t-score because of symmetry. Alright, so the area in the right tail has to be 0.01, and I've got n equals 78. So the degrees of freedom is n minus 1. 78 minus 1 is 77. Okay, 0.01 and 77. Alright, so let's find the 0.01 column. Can't get it all on the same screen here. 0.01 and 77 is not on my table. 77 is closer to 80 than 70, so I'm going to go across and use 2.374. Okay, so my score is 2.374. Right, T sub alpha, and alpha is 0.15. I've got a degrees. Of course, we've got to have another little flip to us. Let's just flip you right back. Don't know why you want to do that to me. Okay, so 0.15, the degrees of freedom, n minus 1. 42 minus 1 is 41. So 0.15 and 41. Let's clean this out. Point 15, we're in this third column. 41 is not on there, but 41 is closer to 40 than 50. So we'll use 1.050. So my score is 1.050. Our last example here. The area in the right tail is 0.005. My degrees of freedom, n minus 1. 93 minus 1 is 92. So 92 and 0.005. Okay, 0.005 is here. 92 is closer to 90 than 100. So we're going to use 2.632. 2.632. Being able to find the critical t-score is a very important part of the problem, and it is one of the only parts that will be new. So if you have any problems with these, please don't hesitate to contact me.